Want to do that again?
This is Team Blue presenting the DIC tensile testing.
Team's objectives include learning how to use DIC and gain an understanding of its capabilities, along with utilizing DIC to find Poisson's ratio. And this will be done while performing a tensile test on 3 different specimens of dog bone shaped samples, with the materials of each of them being polymer, copper, and aluminum. And the main question that the team is faced with is how to use DIC to observe material properties such as forces and displacements, while also being able to measure tensile properties such as stress, strain, and Poisson's ratio. The setup for the experiment included a computer with the GOM correlate software installed, along with a camera and a focal light, which is on the first image to the left. A Mark 10 test stand was also used like in previous labs, which is the second picture. And the 3 dog bone samples or specimens are on the right. And they go from copper, polymer, and aluminum. The experiment included taking dimensions of each specimen, and these dimensions included thickness, width, and gauge length. Each specimen was loaded into the Mark 10 test stand with up to 40 pounds of force, and the displacement created by this force was also recorded. Poisson's ratio was also measured using the GOM software. To collect data, the team started with finding the displacement and load applied to the specimens, which is in figure 1, which shows the force meter or force gauge and the dial gauge on the left. And figures 2 through 4 include stress strain graphs of each specimen, with the 0.2% offset lines for copper and aluminum, and then the 0.02% offset for the polymer. And the data collection also included finding the axial and lateral strains of each sample, along with Poisson's ratio through GOM.
The GOM analysis of the polymer specimen. As you can see from the image on the left, it is the range of the transversal strain, and the max is shown for the transversal strain, and then the image, the right of it, is the digital image correlation, which is exposed to a bunch of different dots, and the GOM software measures the distance that these dots move, and it finds the strain. The image on the right shows the axial strain, and the image next to it is the digital image correlation of that. The figure in the middle, figure 5, this is the transverse to lateral strain graph for the polymer. As you can see, there is a negative linear correlation. As the lateral strain increases, the transversal strain begins to decrease. And from this data, we were able to get that the Poisson's ratio is 0.53, while the literature Poisson's ratio is 0.4, and the percent error was 32.5%. This shows the GOM analysis for the aluminum. On the image on the left, you can see that there is the lateral strain of the aluminum, and the image next to it is the digital image correlation for that aluminum. And then the image all the way to the right would be the transversal strain for the aluminum, and the image next to it is the digital image correlation for that transversal strain. And the image in the middle would be the data plot of the transverse lateral strain. And as you can see, there is a positive linear correlation, meaning as the lateral strain increases, the transversal strain also increases. And finally, we have the GOM analysis for the copper. The image on the right shows the lateral strain for the copper, and the image next to it shows the digital image correlation for that. And then the image all the way to the right shows the transversal strain values for the copper, and next to it is the digital image correlation for those values. In the middle, there is the transverse lateral strain graph for the copper. And from this plot, you can see that there is a negative linear correlation between the lateral strain and the transversal strain, meaning as the lateral strain increases, the transversal strain decreases. And from this, we got a Poisson's ratio of 0.42. The literature value is 0.36, and the percent error is 16.67%.
Using the GOM software calculations, we were able to compare and contrast the three specimens that we had, and we found that the elastic regions vary with each specimen, with copper having the smallest elastic region and aluminum having the largest elastic region. And then we were able to take the GOM calculations and find the Poisson's ratio for each one of them, which you can see was 0.5, 0.5, and 0.42. And comparing those to the real world values, we saw that although they were close to the real world values, they were a little bit off, causing some pretty significant percent error. And that percent error could have been caused by the software we use not being completely accurate. Possibly it just did not pick up on the dots correctly, or it also could have been caused by the way we set up the lab and just poor execution. It's possible that our lighting was not great. It's possible that our data was not great. It's possible that our recordings were not great. But although we were close, there was still some differences between our values and the literature values.
All right. From this experiment, we were able to find the stress and strain for the specimens. The stress was only able to be done when recording from our phones of the tensile machine and taking the values of the displacement and the force. The strain was also able to be calculated from that, but the strain for the digital image correlation, only the strain was able to be calculated. And from this, there were some errors as you stated, and the digital image correlation did not seem to gather all the data for the aluminum sample and the copper sample. From the images shown before, it can be seen that not all plotted points were taken, and this is most likely due to the lighting of the images. And the stress and strain of these materials can be used for specific applications in the real world. For example, if an engineer is trying to build a bridge and there needs to be certain parameters of how this bridge functions and what it's made out of, this test can be used in order to find the stress and strain of specific materials that meet the qualifications for what is needed. And the materials can be narrowed down using this test.
So after using the GOM software and performing this experiment, we can conclude that the GOM software is pretty successful at calculating the Poisson's ratio of specimens. The GOM software was able to measure the displacements, and then it was able to calculate a ratio for every one of our trials. However, the GOM software might not be the best software out there to use when performing this experiment. That being said, digital image correlation is a good way to calculate the Poisson's ratio of materials. If we were to perform this experiment again, we would focus on getting more accurate data. Although we were able to see the displacements, the actual quantitative data was off. And so going forward, the focus would be to decrease the percent error, and that can be done by getting a better setup, maybe trying to find better lighting, maybe trying a different software. Maybe there's better software out there that would actually work better than GOM. These specimens also could have been better. And it's possible that the dot pattern on each specimen was not visible to the camera, and that we might need to get a more visible pattern recognition and pattern on the specimens. And lastly, these are our references.